All right, let's get straight to it. We're looking at a new paper today called LOL, Longer Than Longer, Scaling Video Generation to Hour.
Yep, this is from Justin Cui, Ji Wu, and a whole team of researchers from UCLA, ByteDance, and UCF.
And this paper is a really big deal for anyone working in generative video. It directly tackles this problem called sync collapse.
It does. See, with autoregressive models, think long-live or self-forcing, plus the generation will run for a bit, and then it just shatters.
Shatters how?
It's not just a quality drop. The video literally loops back to the very first frames. It completely destroys any long-term coherence. It's a total failure mode.
And the authors figured out why. They're saying it's a fundamental conflict between rotary position embeddings rope and multi-head attention.
Exactly. They've pinpointed this phenomenon they call interhead attention homogenization.
That sounds technical.
It is, but the idea is that all the attention heads suddenly and at the same time decide to look back at the very first frames. They all get stuck.
So what's their fix?
That's the brilliant part. It's a super lightweight, training-free method. They call it multi-head ropey jitter.
Jitter.
Yeah, they just add a tiny bit of random noise to the base frequencies of the different attention heads. It desynchronizes them.
And that works.
It works. They show the first ever real-time, infinite-length video generation with almost no quality decay. We're talking 12-hour-long videos of jellyfish and wingsuit flyers.
Okay, that's the quick summary. Now let's actually dig into this, because when I hear infinite video, my skepticism meter immediately goes up.
As it should. We've all seen infinite-length videos that just turn into a blurry mess or, a very obvious loop after a few minutes.
Right.
But this paper is different because they're not really building a new model. They're debugging the math of the models we already have.
So before we get to their solution, let's really map out the problem. We're in this shift now, moving from bidirectional models like Sora to these autoregressive ones. Why even do that if they have this huge collapse problem?
It's all about compute. It really is. Bidirectional models, they try to process the entire video at once.
Like a big diffusion unit.
Exactly. The quality is fantastic, but your VRAM just gets obliterated. You can't make them very long. Autoregressive models, on the other hand, they predict one frame at a time.
Just like an LLM generates text, token by token.
Precisely. And they use a KV cache, so in theory, they can just stream forever.
But there's the catch.
There is. And it's these attention sinks, an idea from the streaming LLM paper. To keep the model stable, you have to permanently keep the first few frames in that KV cache.
They're like an anchor to reality for the model.
They're supposed to be. But what this paper shows is that the anchor is actually what's sinking the ship.
So explain sync collapse a bit more. It's not just the video getting boring or repetitive.
No, it's a catastrophic failure. If you look at the attention scores for the first 100 frames or so, everything's fine. The model is looking at the recent past.
As it should.
But then, bam, at a very specific frame, they mention 132 or 201, the attention scores for those first few sync frames they go vertical.
Vertical.
I mean, they spike through the roof. The model completely stops looking at the frame that just happened and puts all of its focus on frame 0.
And visually, what does that look like?
You could be watching a video of a log in a forest, and it suddenly just snaps back to the exact same pixel configuration it started with. It's a perfect, unbreakable loop.
And because it's autoregressive, once it's seen frame 1 again, it's just going to predict frame 2 again.
And you're stuck. Groundhog Day. The model is trapped.
The fact that it happens at these specific intervals, regardless of the prompt, that's the key clue, isn't it?
Absolutely. It means it's not the model getting confused by the content. It's a structural problem. It's a bug in the positional encoding itself.
Which brings us to Ropey. Most people listening are probably using Roki in their models. It's the standard.
It is.
We know it works by rotating the query and key vectors. So why is that rotation causing a system crash?
Because rotations are, by their nature, periodic. If you keep rotating a vector over and over, you're eventually going to get back to where you started.
Okay, but I thought Ropey used different frequencies for different dimensions to try and avoid that exact problem.
It tries to, yes. But the authors found something they call intrahead phase concentration. Even with all those different frequencies, there are still points in time where the phases just happen to align perfectly.
So at that moment, the model thinks the sync frame from the beginning is mathematically the most similar thing to the next frame it needs to generate.
That's it. The dot product attention score just explodes. But here's the really crucial part of their investigation.
Go on.
Previous work, like iFlex, assumed this was just a temporal problem, just an issue with the time dimension.
And iFlex worked pretty well for bidirectional models, didn't it?
It did. But when this team tried Archiflex on an autoregressive model, it failed. The collapse still happened.
So it wasn't just time.
It was something deeper. And that's what led them to the big aha moment: inter-head attention homogenization.
Homogenization? That just sounds bad, like all the diversity is being erased.
That's exactly what it is. In a healthy transformer, your different attention heads are supposed to be looking at different things, right? Head A tracks motion, head B looks at texture, head C looks at the background.
Right, they're specialists.
But at the exact moment of collapse, they found it wasn't one head failing. It was a synchronized failure.
Wait, so head A, B, and C all just decide to look at frame 1 at the exact same time?
Yes. The attention diversity completely collapses. They call it a global degeneracy. The heads all start screaming, "Look at the beginning!" And the model has no choice but to obey.
That's a fascinating find.
Yeah.
It's like that classic example of soldiers marching in step across a bridge.
It's a perfect analogy. The individual vibration isn't the problem. It's the fact that they all resonate at the same frequency. The Rotary periodicity is that marching beat.
So if that's the problem, how do you fix it? How do you tell the soldiers to break step?
Well, this is where the paper gets so good. Usually a fix for something this fundamental means a whole new architecture or months of retraining.
Right. Throw out ropey, use something else.
But they don't do that. Their solution is called multi-head ropey jitter, and it's an inference time patch. No training needed.
Jitter makes me nervous. I hear jitter, and I think you're just adding noise. And adding noise to inference usually just degrades the output.
It is noise, but it's very targeted, very structured noise. Instead of every attention head using the same base frequency, usually 10,000, they give each head its own, slightly different base frequency.
Okay, walk me through the math on that.
The formula is pretty simple. You take the base frequency, let's call it theta 0, and you multiply it by 1 plus a small random number unique to each head.
So head 1 might be operating at a frequency of 10,050, while head 2 is at 9,920.
Exactly. And by doing that, you completely desynchronize their periodic resets. Head 1 might want to look back at the sync at frame 201, but head 2 is on a different cycle. Its reset isn't until frame 215. Head 3 is somewhere else entirely.
So you never get that choir effect where they all scream at once, that failures get smeared out over time so the overall attention stays stable.
You got it. You prevent the constructive interference of the error.
But I'm still skeptical about the quality. If you're messing with the frequencies, aren't you messing with the model's understanding of position?
A very fair question, and that's why their ablation studies are so important. They tested this on a 1.3 billion parameter model.
Okay.
And they measured two things: sync collapse max, which is how bad the looping is, and dynamic degree, which basically asks, is the video actually moving or is it a still image?
So what happened when they tried the other standard fixes? Like position interpolation.
PI. It's the standard for extending context in LLMs.
Oh,
and
yeah.
it did fix the collapse. The video didn't loop,
Right.
but the dynamic degree went to almost 0.
It generated a photograph.
Pretty much. Just killed all the motion. Then they tried just changing the base frequency. Maybe 10,000 is a bad number. Let's try 20,000.
The classic engineer's fix. Just double it.
And it didn't work. It just moved the collapse to a different frame number. It didn't solve the underlying resonance problem.
Okay, so tell me about the jitter settings. You said it was structured noise. How much noise?
This is the key insight for anyone wanting to implement this. They have a scaling factor, sigma, and it's very sensitive.
How so?
If they set sigma too low, like 0.1, it wasn't enough jitter. The heads were still similar enough that they'd eventually lock back into sync and collapse.
So you need enough chaos to actually break them apart.
Right, but if they set sigma too high, then your original concern was right. The video quality started to degrade because the positional information got too scrambled.
So what's the magic number?
0.8. At a sigma of 0.8, the sync collapse score plummeted from around 70 down to 16, basically gone, while the dynamic degree, the motion, was identical to the baseline.
No quality loss, no crash.
None. They completely decoupled stability from motion dynamics.
What about the sync frames themselves? Did they try just getting rid of them? We're adding more?
They tried that too. Increased them from 3 to 5, decreased to 1. It made absolutely no difference.
Which proves the point, right? It's not about the content of the first frames.
Exactly. It's a pure positional artifact. The model isn't collapsing because it loves the first frame. It's collapsing because the math is telling it that the position of frame 201 is the same as the position of frame 1.
That's a huge relief, actually.
Yeah.
It means we don't have to spend time engineering the perfect anchor frames. We just need to fix the coordinate system.
Correct.
Okay, we have the fix. Let's talk results. They claim 12 hours. What does a 12-hour AI-generated video actually look like?
So they showed a few examples. One is a wingsuit flyer going through a mountain range. Another is jellyfish drifting in the ocean. And the main thing is the video stays locally coherent, meaning the edges are sharp, the motion is smooth second to second, there are no loops, no weird jumps. It looks like a real video playing.
But there's a but, isn't there?
Of course.
Yeah.
There is no global consistency. This model doesn't have a long-term memory or a story Bible.
So the wingsuit flyer.
The wingsuit flyer's suit might change color every few minutes. The mountains in the background might slowly morph into a cityscape and then back again. It has object permanence issues.
It is the memory of a goldfish, but the stamina of a marathon runner.
That's a perfect way to put it. This is infinite streaming, not infinite storytelling.
And this is all possible because they generate everything on the fly, right? The noise, the Rotary embeddings.
Yep. Using a 3D causal VAE decoder, you don't pre-calculate anything. The jitter is applied dynamically during inference.
Which makes it incredibly efficient.
It does. The compute cost of the jitter itself is tiny compared to the attention calculation.
And what about the base model's own flaws? If the underlying model isn't perfect, this doesn't fix that.
No, and that's a key limitation. LOL stops the collapse, but it doesn't stop hallucinations. If the base model tends to generate, say, six-fingered hands, this will just generate six-fingered hands forever.
If you have a bad model, this just lets you watch it fail infinitely.
A bit harsh, but yeah, true. But think about the applications for ambient video. Dynamic wallpapers, generative art installations, nature streams. For that, this is a total game changer.
So on the implementation side, if I'm an engineer listening to this, how hard is it to drop this into my own transformer?
It is shockingly easy. It's practically a one-liner. In your model's forward paths, wherever you calculate the ρp frequencies, you just inject that little randomization formula. You don't touch the weights. It's a pure inference side change.
That's so rare. Most breakthrough papers require a complete overhaul and a month of GPU time.
It really is. It shows that sometimes the solution isn't more data or a bigger model. Sometimes you just have to detune the resonance frequencies.
It really makes you wonder, doesn't it? If jittering attention heads fixes this huge show-stopping bug in video models, what other problems in AI are secretly just resonance issues?
That is the big question to take away from this.
I mean, think about LLM hallucinations. When a model gets stuck in a repetitive loop, just saying the same phrase over and over.
We've all seen that.
Is that a failure of logic? Or is it just another case of positional resonance, where the attention heads get locked onto a specific token?
It's entirely possible. Desynchronizing the heads could be a general technique for improving robustness in all kinds of models, not just for video.
So the lesson is we need to introduce a little bit of chaos to maintain stability.
Controlled chaos.
Yeah.
The sigma equals 0.8 level of chaos.
Right. Don't go setting the lab on fire.
Exactly.
The paper is LOL longer than longer. If you work with long context transformers in any capacity, it's a must-read. Just the analysis of the interhead homogenization problem is worth your time.
Absolutely. It's a masterclass in diagnosing the math instead of just throwing more compute at a problem.
We'll have the link in the description. Thanks for tuning into the AI Paper Podcast.
See you in the next one.